Anyway, good to have you here, and your topic is opportunities and challenges for metallurgy. If you're willing to take it.
Thank you.
Thank you.
Well, I appreciate the invitation to share some of my observations. So I said this morning, I wish Brian were program manager in the United States because he would sponsor experimental research. Yes. Well, I don't want to dwell upon these challenges, but clearly we've had enough discussion of need for green energy, recycling, climate challenges, and pollution. And clearly the materials have to be operating at higher temperature, be lighter and stronger. And there are evolving approaches, all of which are receiving a lot of attention, and they have their own benefits and deficiencies. In the United States, they're getting more attention than the experiment, unfortunately. And so I'm going to share two contemporary examples where I've used classical physical metallurgy, the strange field that's not so popular anymore in the States, and conventional nucleation theory and CalFAD to show how you can really advance the field. The first example deals with primary crystallization in amorphous alloys. This includes both aluminum and iron-based systems. And one of the key points here is to recognize that these solid solutions or amorphous phases are not homogeneous on the atomic scale, but there are spatial heterogeneities. And recognizing this allows us to understand the nucleation properties. And then ultra-high temperature refractory metal alloys, as we're reaching the limit of capability with nickel-based alloys, we have to go to higher temperatures. There are some ceramic developments, but there was a famous person, Chet Sims from General Electric, who one time commented about ceramics, dust to dust. You start with dust and you end with it. And here, again, we're using physical metallurgy and computational thermodynamics to develop what I would call a refractory metal superalloy. All right, so glass formation requires bypassing nucleation and growth. And you can do it either with nucleation, such as window glass, or with growth control. And here, you recognize that the maximum growth rate is above the nucleation rate in terms of temperature. And so you can quench in a material that has either some quenched in nuclei or growth inhibited phases. And that was what we thought aluminum alloys were like. And Lindsay put together this compilation and shows that the amorphous alloys, when they're partially crystalline or nanocrystalline, I'm afraid to use this pointer, actually go beyond the conventional alloy islands into the engineering ceramics. So these are very attractive, being lighter and stronger, and on a specific scale, approaching steels. And this is the typical crystallization reaction. The primary crystallization is one where you get this aluminum in an amorphous matrix, and because of the very high density of nanocrystals and the rejection of yttrium and iron, the growth is inhibited so that you can maintain that size. And you can see before final crystallization, you have about a 75-degree temperature range up to about 350 or more. And that's pretty good for an aluminum alloy. And it clearly has to be heterogeneous nucleation because our compositions are hyper-eutectic, and you would expect some compound to form, like in aluminum samarium. And the driving force for formation of aluminum is half that for the intermetallic phase. So there has to be some heterogeneous nucleation site to promote the primary aluminum. And that turns out to be spatially heterogeneous groupings. And these are dynamic groupings. This is a computer simulation from Sharon Glosser. But we have seen them in actual practice. And that's with a colleague of mine, Paul Voiles. We use fluctuation electron microscopy. And if you have a situation where you have a spatially homogeneous material, then the fluctuation electron microscope image is mostly uniform in its intensity in the dark field image. But if it's spatially heterogeneous, you have groupings of atoms that are close together, then you're going to get intensity variations. And by analyzing the intensity variations, you can back out what the type of clustering is and the density and numbers, the size and number density. And we've done that for these aluminum amorphous alloys after they've been quenched into the glassy state. And it turns out that they're aluminum in their medium range order. So what that looks like is this. We have an aluminum-rich region which is not crystalline, so we get some constructive interference, but not enough to give diffraction spots. And the solute atoms, iron and yttrium and others, are outside. And so this is different than what other people have talked about with solute-centered clusters. These are naturally occurring. And it's not surprising since this has more than 88% aluminum, so you would see this. But it's still amorphous. And so we want to account for the crystallization behavior, and we measure the number density as a function of time at different temperatures. And so this is our model. We have this aluminum-rich region that's a medium-range order. It's about a little bit less than a nanometer in radius, and it's surrounded by this nanocrystal. So we replace the amorphous MRO interface with a nanocrystal amorphous interface and a nanocrystal MRO interface. But that's very low in energy. And you can go through the seeded nucleation behavior. And with this, you replace those interfaces. And because the MRO takes up part of the volume, it's a very effective heterogeneous nucleation site. And it's chemically the same as the nanocrystal. So we have complete wetting. So it acts as a very good seed. And when we go through very carefully the interfacial energy using Franz Papen's model and the driving free energy, which required a full CalPad evaluation, not just a simple undercooling approximation, we find that the critical size is about 1.3 nanometers, which is, of course, bigger than our core, 0.96. And using the free energy and the interfacial energy, we find that the barrier to nucleation is about 33 KT, which is all reasonable. And so my student came to me, he was very excited. It fits. My calculation fits the data. I said, yes, but it's on the wrong side of the peak. We're heating up, and your points match the calculation on the high temperature side. What's going wrong? Well, I want to remind you that we didn't start at zero time. In other words, you put your sample in and start annealing. There are no nanocrystals that form initially. It takes some time before the first ones appear. This is a delay time. And so this tells us we have transient nucleation. That's very important. And that actually is the main reason that this forms a glass. And so we had to measure the delay time. Well, you can extrapolate the linear portion, but that's kind of uncertain. So we used nanocrystallization studies in a nanocalorimeter. Mettler produces this flash DSC. And by going at higher heating rates, you can build up the glass transition very nicely. And you could see that the Kissinger plot of glass transition versus primary crystallization allows us to separate the two. And then when we anneal samples, we looked at them at different times. And measuring the glass transition, we have one slope that is associated with the structural relaxation in the glass. And then once the nanocrystal appears, composition of the amorphous phase changes, and we get a different slope because the glass transition temperature changes with annealing. And so that break point is a very accurate measure of the delay time. So using that, we've shifted the curve to lower temperatures, and now we have very good agreement. The curves fit our experimental points very nicely, and we've gone through the whole analysis, carefully documenting each step. And when we do that, we have, Lindsay should be here, an independent test of plotting the log of the nucleation rate times the delay time versus delta G star over KT. There's good agreement between the theory and the experiment. So classical nucleation theory works, but you have to evaluate the parameters carefully. A lot of people take gross approximations and they say theory failed. Well, that's not quite true. Okay. So the motivation for high temperatures is shown here. And like Brian, this is my most highly cited science paper. It gets not thousands, but hundreds of citations. And it's clear that putting more effort into increasing the operating temperature another 10 degrees, which would cost $1 billion and only returns a few million in profit, you have to question whether we're going to push these nickel-based alloys much higher. They're already operating above their melting point, and only because of the thermal barrier coating that they survive, and of course the internal cooling. So one of the systems we've been looking at as part of a RPIT program is the moly-silicon boron system. Here there's a black triangle between a molybdenum solid solution and MO3Si phase, and a ternary intermetallic MO5Si B2. This phase is very densely packed and has a very high melting point. So the liquidus temperature is above 2100 degrees Celsius. So these alloys have excellent high temperature properties compared to the latest generation of nickel-based superalloys. These are orders of magnitude lower in creep rate. However, they have limited ductility and undergo a ductile brittle transition. Their oxidation resistance is good, but not great enough. The recession rate is a little bit too high. So these are issues that have to be solved. And I want to point out that the T2 phase, this ternary intermetallic, is not a line compound. It has a width to it, a homogeneity range. All right, so these are the issues we have with room temperature ductility, low temperature oxidation. There's pesting that occurs. You get excessive oxidation until the coating, the borosilica forms. High temperature oxidation with excessive recession. Relatively high density, molybdenum is over 10, whereas the nickel-based alloys are around 9 grams per cubic centimeter. Resistance to microstructural modification. The problem with these very high temperature alloys, once you make them, you can't change them. You want phase stability at high temperature. That means you can't do diffusional processing and manufacturing components. So we've solved each of those problems. The first is using what I call the Hume-Rothery rules of intermetallics or silicides. We have a size difference in electronic factors that allow us to predict solubilities with good accuracy, Brian, actually. And then we've looked at the literature, and there's reports that the problem with the molybdenum silicon boron is the silicon. Silicon is the most potent solid solution strengthener in molybdenum. We have too much strength, so we have to reduce the silicon content. But how do you do that when you have a guaranteed solubility? Well, we go to the other side of the phase diagram, which has much lower solubility. So we've reduced the solubility from 2.6 to 1.75, and that improved the ductility. And we compared alloys N3, which is molybdenum T2 MO2B side, and C3, which is the molybdenum MO3Si T2 side. So they're just on both sides of the two-phase field between molybdenum and the T2 phase. And when we did that, we found not only did we reduce the solubility, but we got precipitates of molybdenum in the T2 phase. That's because as you go up in temperature, entropy opens up the T2 phase, and so as you cool down from the melt, the T2 phase is supersaturated with molybdenum. And so as you anneal at 1600, you actually precipitate molybdenum inside the intermetallic, which is sort of the reverse of what we normally think of. So instead of precipitation hardening, we get precipitation toughening. So the molybdenum precipitates in the T2 phase, arrest crack growth. And as a result, our toughness went up based on crack formation. So it's around 15 to 17 MPa root meters versus 9 for on the other side of the phase diagram. And that puts us in the range where we had about 50% molybdenum solid solution. So the toughness is up with the best alloys that have been produced by powder metallurgy. All right. So now we have to make these, and our RPE program is called Ultimate, and here we're using additive manufacturing to make components that will eventually be turbine blades with an increase in operating temperature of 200 degrees for a 10% efficiency gain, and we're supposed to reduce the cost by 20%. Well, one of the challenges with additive manufacturing is that most of the papers are dealing with alloys that are readily available in powder form. Titanium 6-4, various stainless steels, some Inconel alloys. But is titanium 6-4 the best alloy for additive manufacturing? I doubt it. But how do you do screening of different alloys when you have to rely on alloyed powder? It's very expensive to do a powder run. Well, you can take elemental powders and try to melt them, but if you have things with vastly different melting points, titanium and aluminum, your composition control is kind of tricky, because once you're melting one component, you're vaporizing the other. So how do you do this in a reproducible fashion? Because additive manufacturing is perfect for doing high throughput screening, if you could do it. And so we thought of, or I thought of using thermodynamics again, and just reaction synthesis. So I take silicon nitride, boron nitride, and molybdenum, and I can produce any alloy I want in that three-phase region. This is an example where we form the T2 phase, MO5 SiB2, and releasing nitrogen. Okay. If I want other phases, I add a little bit more molybdenum or more boron nitride, and I can balance out and get any composition in the phase diagram. All of these components have similar melting temperatures, so I'm not going to lose anything. The only thing I lose is nitrogen. And of course, nitrogen has very limited solubility. So, and these powders are pretty cheap compared to pre-alloyed material. And this is what we've done with directed energy deposition. There are hoppers. These are the feed stock, and we get a fairly uniform fine grain size. That's a 10 micron scale marker. We get the right phases. We get titanium boride at the build plate, at the plate, and you can cut that away, so it's not a big problem. Compositional uniformity we've added titanium as well, but over millimeters. These are thousands of microns. So the uniform. And that's going from the bottom to the top on the build. The other advantage is that we had to reduce the density to below 9. So we added titanium, and my colleagues at Computherm pointed out that with 10% titanium, we can even reduce the silicon solubility further. So now it's over here, it's about 0.2%. More titanium doesn't help us because it pushes this out again. So 10% titanium satisfies the density profile, which they've calculated, and we can now produce samples with this composition that have about 1.5 gigapascals of strength. and ductilities of more than 20%. We're now preparing samples for creep and fracture toughness and thermomechanical fatigue. So, again, with the application of alloying fundamentals and innovative processing, we've overcome all the challenges in the polysilicon boron system. Room temperature ductility, toughness, low temperature and high temperature oxidation resistance. I didn't talk about it, but we have a coating that takes care of that. Density guided by computational alloy analysis and manufacturing. So I think out of this program we'll get a refractory metal superalloy that'll replace the nickel and allow us to really improve the efficiency of these engines and power output. And thank you for your attention. Oh, I forgot one other thing. Okay, so what's the future? This just came out in the MRS bulletin. So we hypothesize and experiment and analyze, and they show arrows going in one direction, but I think the analysis and the experiment people talk to each other and refine the hypothesis, as Brian pointed out. With autonomous, which they would call a self-driving lab, we maybe hypothesize, but you'll see the arrows go both ways. The experiment, you take the person out of the experiment now and put a robot in there that prepares the alloys, processes them, and analyzes the microstructure, analyzes it according to some algorithm, image analysis or whatever, and reports the data. And the data go back through additive artificial intelligence or machine learning. They go back and forth, and I don't know how they have refined the hypothesis, but there's no person involved in this.
Is that a trash can?
Yes. Yes. But you see, the person is taken out of this, and I think Brian really hit the mark exactly, because discovery is a human characteristic. We should not forget that. If we're going to save the world, we better not rely upon these guys. Thank you.
Thank you very much. Questions?
So thank you very much. Very interesting work. Can I ask, you mentioned in the beginning that the molybdenum silicon boron alloy has low oxidation resistance, and at the end you said...
Oh, no, it has oxidation resistance, but the recession rate, that is the diffusion of oxygen through the scale, the borosilica, reacts with the underlying alloy to a too great an extent. We've addressed that by changing the boron to silicon ratio in the coating and adding a little bit of aluminum oxide. So we've annealed samples in air at 1700 degrees Celsius for days, and the weight change is 1 milligram per square centimeter, which is negligible.
Yeah, that's impressive. And how about, you also mentioned the higher density compared to the nickel superalloys.
Right. Current nickel superalloys are approaching 9 because they add a lot of tantalum, rhenium, ruthenium, heavy elements, and those are present in a couple percent, not just minor additions. So the density is about 9 for the current generation of nickel-based superalloys. My density is 9. I brought it down from 10 by adding titanium.
Thank you.
I think it was oxidation.
Okay. And there's a question here, Gary.
John, how about the effect of cooling rate on these alloys? Have you studied the effect of...
Well, the grain size is pretty fine.
This is on the DED though, right? So that's pretty...
Well, we've done laser, well, the tensile samples were made with laser powered bed fusion.
Oh, it was LPBF.
Yeah. But the composition control is pretty good.
Yeah.
And that reaction synthesis works very nicely.
Okay, well thank you very much, John. And so we did indeed get our our three alloys. We had we started off with the Badisha alloy, and then we moved on to the Cantor alloy, and we finally ended up on the Perepezko alloy. So I guess you have to pay your money and you take your choice. One other quick point, we had a discussion last night, I think, and I'm a great believer that we review those papers that are hot topic papers. I actually believe in the reverse, which are the real papers that really matter, are what they call the slow burners, the ones where you do something and then nobody realizes how important it is until much later. So we saw some good examples of that today, I think. And I'm going to end with one little joke, which I think is a slow burner joke. It often doesn't work. So but I'm talking to an audience, so we've had Googles and trillions and gazillions and so on. So I think it'll work today. So I'm going to try it. And if it doesn't work, I'll quietly exit the room. And this is this was in the Trump era, and the chief of staff, unfortunately, there was a military incursion, and two Brazilian airmen died. And so in the morning, they spoke to Trump and they said, "I'm sorry, but I've got really bad news. Two Brazilian airmen have died." And he said, "That's terrible, terrible. You should have got me up in the middle of the night. You should have told me. This is really serious." And then he said, "And how many is a Brazilian?" so on that note, I'll leave you. Lunch is...